Hello boys and girls, this is Lorenzo here, and welcome back to another episode of Lorenzo's Lessons of Space. Today we are on episode 7, and we are going to talk a little bit more about orbital mechanics. The title for this episode is very aptly Orbital Mechanics 102. Reason for recording this video is a question by a viewer named George. He asked, after viewing the Orbital Mechanics 101 video, he asks, what happens when you burn straight towards a planet or straight up from an orbit? Does just the shape change? Do you crash on the planet? What happens to the orbit? I explained him a little bit in the comments what would happen, but I told him I'd make a video as well. So we're going to answer that question and expand a little bit on our basic understanding of orbital mechanics. So here we have our spacecraft. It's a simple craft with a tank and engine, a cupola command pod that has some windows in it for Jebediah. It doesn't really matter for us, but now the poor little guy can look along as we maneuver him around space. So before we move on to the more advanced topics of orbital mechanics, a quick recap. As I explained in the episode 2 of this series, the orbital mechanics one, orbiting is basically falling towards the planet while going sideways fast enough so that you perpetually miss the ground. Now here on the map view we can see this. Our spacecraft, the Orbiter 102, is in a fairly circular orbit around Kerbin. The highest point, the apoapsis, is 310 kilometers, and the lowest point here, the periapsis, is 302 kilometers. So it's not quite a circle, but near as makes no difference. It's a zero inclination orbit. This means it's along the equator of Kerbin, and this means the spacecraft is falling directly towards the center. You can understand this because it is now falling towards the center, and it will then again end up here, and then it will fall back to here, and it will continue to do that. While it's doing that, it's doing the same thing on this vector. It's falling from here to here and from here to here. These two vectors combined make the orbit into a circle. This might not make intuitive sense, but for me, understanding an orbit as a two-vector pendulum movement makes intuitive sense after thinking about it for a little while. If you would remove the surface, the atmosphere, the things to crash into, and just throw up a ball, so we have now some phantom gravity with no substance to crash into, throwing up the ball, it will go up, fall down, but it has speed now, so where the ground would be, there's no ground, no obstacles, it would go down past the center of gravity, an equal way up as you threw it, and then it would pendulum up and down perpetually. This is what happens in an orbit. Instead of it happening in one dimension, it happens in two dimensions simultaneously, and that is what makes it a circle. Now, of course, when there is a planet, when there is ground, when there is atmosphere to crash into, this is the only way you can do it. If you try to do it in the one dimension, just throwing something up, it will come back down, and before it can pass the center of gravity, it will hit the atmosphere, hit the ground, and come to an abrupt stop, with or without explosions, of course. So the two-dimensional orbit, the circular, the elliptical trajectory is what we need in real life in this space game. So remember, an orbit is a pendulum movement, an oscillation in two different dimensions. We're going left and right perpetually, and we're going up and down perpetually, and this makes a circle going this makes a circle around the planet, which is not perturbed by atmosphere or by rock, which is below it. So it being an oscillation, from that it follows that without the application of thrust, a spacecraft will return to the same point on the orbit. This is a property of it being a circle, of course. It's not some weird spiral, it's not going out of control, it's a closed circle. So you can understand that without the application of thrust, you'll return to the same point on that orbit. Perhaps intuitively. From this premise follows that if you make a change on any point of the orbit, most of the effects of that change, of that burn, will occur on the opposite side of the orbit. Remember, as soon as you shut off your engine, you're not applying thrust anymore. You have to come back, you will come back to that point in the orbit. From this it follows that the point where you perform your thrust cannot change that much. while you're performing thrust, of course, you're not returning to that point because you are changing the orbit. But when you perform your thrust, when you stop performing your thrust, you will return to that point in the orbit. So all that energy will be put on the other side of the orbit. Now, this game here, I mean, we've been looking at the map view now for a few minutes, quite boring perhaps. So here's a view of the planet. Going right back into the map view though, we're in school, we're not in picture class, we're here for the orbital mechanics, not for the pretty pictures. This game supplies a very useful tool. It's called the maneuver node. We click add maneuver and we get a little circle with lots of icons, and these icons allow us to simulate a rocket burn. The yellow one here, this is the prograde marker. This simulates a burn in the direction of travel. Incidentally, the icon is painted in the direction in which it will simulate the burn. The opposite one, the yellow circle with the cross in it, is a braking maneuver, a retrograde marker. We've covered this in the previous episode a little bit, but we're going to go over it again. Burning prograde will increase your orbit, will make you go higher. As you can see, if we make a prograde burn here, the altitude of the orbit on the opposite side will increase. As we're accelerating here, we are going in this direction, in the prograde vector, the vector we are traveling, and this will fling us around higher here. Incidentally, it will also be going slower. We touched on that in the Orbital Mechanics 101 section. If you don't understand how this can be, I recommend you watch that. But a higher orbit equates more energy but a slower speed, because you are still circling the planet and your trajectory has just become a lot longer. So burning here, prograde, increases the opposite side of the orbit. Now if you want to make it circular again, you have to do a second burn here on the high point, go prograde again, and then you will raise the opposite, which is incidentally then where you started your maneuver. So in 2 maneuvers you can raise your orbit, and this is the most energy efficient way. Now of course opposite it works as well. You can also make your orbit smaller by braking, and this, the way of going closer to the planet or going further away from it, then revolve around burning prograde or retrograde. So this is not intuitive at all. If I want to go to the planet, I burn retrograde, in the way I'm not in the opposite way I'm traveling. So I'm burning parallel to the surface, yet I am going to the surface. This is the unintuitive thing about orbital mechanics. Now here comes the question that George asked me. He's like, what happens if you do burn straight towards the planet? We can turn the rocket like this, and it might seem intuitive that if we ignite our rocket like this, we are going to go careening into the surface. Now a little side note here, if we fire our rocket, if we have a very big rocket and we fire it a lot, we will of course hit the planet. If we apply that much delta V that we cancel out the fact that we're going sideways fast enough not to hit it, we will hit the planet. But this will require a lot of delta V and is very inefficient. You will understand if we apply some kind of warp drive and go straight forward, we are going to hit it. But in regular orbital mechanics, this is definitely not the way to hit the planet if that is what you want, and we can see here why. We add the maneuver node, and we are going to use this blue circle. This is the axial movement. We are moving at 90 degrees to the direction of travel, which incidentally in an orbit is either straight towards the planet or straight away from it. So remember what I said, any movement will affect the orbit most on the opposite direction. This counts for prograde. We are now applying thrust in a 90-degree vector, so if we start doing that, let's see what happens. As you will notice, here on the point where we are applying the thrust, hardly anything is happening, because as soon as we cut this thrust, we are going to have to return here. We are still in an orbit. So what is happening? Our periapsis at 90 degrees from the current point will get closer to the planet. We are going to get closer, but the amount of fuel required to get this close is exorbitant. It's a lot higher than it was if we were to just simply brake. Say our goal is to get to an altitude of 100 kilometers, well, call it 94. If we want to achieve that by burning straight towards the planet, we would require 590 meters per second of delta V. Now we can, using this maneuver node system, quite easily compare that to a braking maneuver. If we just brake and we want to put our periapsis at 100 kilometers, let's make that node here, 145, 103. So that's the ballpark. We only require 103 meters per second of delta V. So that's about 4 times less. Now you might imagine, why is this so inefficient to do it like this? So we make the maneuver node with the axial burn again, and something else apart from the lowering of this periapsis is also happening. This apoapsis is being raised tremendously. This is because we are not applying all our energy to going back to the surface. We are applying the energy into going this way, into going through the planet, as it were. We cannot go through the planet, but we still have a sizable sideways velocity component. So while we're getting closer to the planet on this side, we are we're going higher on the other side. So that's what a 90-degree axial burn does. It reduces the periapsis while simultaneously raising the apoapsis, and doing so in an inefficient manner. Now, if this is the exact orbit you are looking for, this could be a valid burn. And just to intercede myself here, of course, if you do it the other way, burning away from the planet, the opposite effect happens. The apoapsis becomes higher on the near side in 90 degrees direction, and the periapsis becomes lower on the far side at 270 degrees from the current orbit. Always in orbital mechanics, if you do one thing and understand what happens, the opposite thing will do the exact opposite. Action is reaction and all that. So back to our maneuver here, lowering the periapsis to 100 kilometers while raising the apoapsis to 680 from our 300 kilometer orbit. If we want to do this, using this maneuver, it's about 580 meters per second. This is a single burn. We can do this more efficiently in 2 retro or prograde burns. So if we do 1 prograde burn to raise the apoapsis to, what was it, 680 kilometers, that would cost us 158 meters per second. Fine. If we then wait until we are at this apoapsis, make a maneuver to slow down again, and then reduce our periapsis to that number of 80 something. It was about 100 if I recall correctly. This, I'm not sure if it will tell me the amount of delta V. It will not, but I will promise you it's less, and we will find out by actually doing the first maneuver node. And you can see the 1 burn solution, by doing it in the actual way, was 580 meters per second. So now we are going to find out how much the 2 burn solution is. So let's have a quick go at that. Time warp to the maneuver node and fire up the engine to apply 158 meters per second of delta V. And there we are. Now we can remove this maneuver node and see how much delta V this one is. This is 122, so combined that's about 270-280 meters per second of delta V, as compared to 580 doing it the anti-normal way. Not the anti-normal, the actual or anti-axial way. Now the question, why is this inefficient? As I said, it is most efficient and indeed easiest to change a point on your orbit that is directly opposite on your orbit. Now, while burning in this axial way, you are changing 2 points at once from a point that is not opposite in any way. So this will cost you more energy for no real gain whatsoever. Now this burn I just did here was to attempt to re-establish a somewhat circular orbit, because my examples work a lot better from predictable circular orbits. So with a burn straight towards the planet or straight away from the planet, you are going to change your orbit in the same plane, modifying your apo and periapsis simultaneously. While completely possible, this is a very inefficient way of doing things. Of course, there are, in the real world especially, valid circumstances in which you would want to do this. You are combining two maneuvers into one burn. This will save you time, this will save you rocket re-ignitions. In the game this is not a problem, you can reignite any rocket as many times as you like. In real life this is not so, it's quite a complicated manner to reignite a rocket in space, and of course with longer orbital periods a mission will take a lot longer if you do multiple burns. These real life concerns might necessitate making a burn to or away from a planet, but the delta V expenditure is so huge that most missions don't do it. So, to recap, it's almost always better to use the prograde and or retrograde markers to modify an orbit. To make a shape you require, you might require two burns, one to raise the apoapsis, and then at that apoapsis another burn to raise the periapsis to the desired point. And using this two burn system, this is called a Hohmann transfer, this is the most efficient way of changing an orbit in the same plane. Now, I've mentioned the plane of an orbit once or twice already, and if you recall, way in the beginning of this video, I described an orbit as a two-dimensional oscillation, a two-dimensional pendulum effect. And you can see here in a three-dimensional world, the planet is 3D, the space is 3D. The orbit can be described as a two-dimensional slice in that. If you fill in this circle and expand it, you get the plane that the orbit is in. If you're in it just for the orbit, the plane is not that relevant. Of course, if you want to orbit over different areas of the planet, you are going to have to incline your orbit, as that's called, basically tilting the plane through various angles. Now, if you are doing it if you're launching from the planet you will be orbiting, you can control the inclination of your orbit a great deal by choosing the direction in which you launch. And for Kerbin, this is very much the best way to control inclination, because inclination changes in space are incredibly costly in delta V. Nevertheless, they can be necessary. For instance, if you want a rendezvous with a moon like Minmus, you can see here the orbit here, the equatorial orbit around Kerbin, and the orbit of the moon have the same plane. This is made intentionally, makes the game a little bit easier, so you can just launch straight east from the space center, go into an equatorial orbit, expand that orbit. So you could do it like this, expand the orbit. Oh, whoops, I'm doing it a little bit, overdoing it a little bit. Expand the orbit and meet up with the moon. Let's see if we can actually make that happen. It should not be too easy. Yeah, there we go. Have an intercept with the moon. Plotted it right there. So that's very easy. Of course, for different celestial bodies, they can very well orbit in a different plane. You can see it here. They are not aligned with the plane of the orbit of our spacecraft or the moon. And if we were to go to Minmus, we are going to have to do an inclination change. An inclination change maneuver happens like so. These purple icons on the orbit represent going straight up or going straight down. And just to show you here in the flight scene, we are now pointing in the direction of travel. This is prograde. We are now pointing straight towards Kerbin. This is down, or axial burn toward relative to the vector of movement. But of course we are in 3 dimensions, even though we are in a 2-dimensional orbit. This is also quite possible to point up towards up relative to the vector of movement. We are now effectively moving sideways, pointing up perpendicular to, or no, parallel to the surface of the planet. And of course it is also very possible to do burns in this direction. What this will do with your orbit, it will change the tilt, it will change the plane of that orbit. You can see it if we simulate a burn like this. You can see the orbit will incline. And this can of course be useful if we want to scout the land under this bit, or under this bit, or if we want to match up with Minmus. Now this simple change, the orbit doesn't even change that much. It's already 300 meters per second of delta V. So inclination changes in your space program, you want to minimize them because they are among the costliest moves in the game and in real life as well. Inclination changes are very expensive, as I said. I will show you how to make an inclination change to rendezvous with the moon Minmus here. This is inclined to about 5 degrees. Not a huge deal, and it's also fairly close to Kerbin, so you can get encounters with Minmus without doing your inclination matching burn, but it's good practice to do it. And you see I set Minmus to the target, set it as a target, and this now gives us 2 additional markers, the ascending node and the descending node. These are the points where the planes of our orbits match. I want you to imagine 2 hoops. One is slightly smaller than the other, so it fits inside, and you're going to tilt it in random ways. While they're tilted inside one another, they are not in the same plane, but they will have 2 points where their circles touch, overlap, or they would overlap if the orbits were the same size. These 2 points are the ascending node and the descending node. Now, to match the inclination of these 2 orbits, you want to perform a burn at either of these points. So we're going to plot a maneuver node here at the ascending node. We're going to use the purple markers, and we're just going to eyeball it when our blue orbit will have the same plane as our yellow target orbit. So if we reduce it, here we are tilting it, and we can see here with this burn the inclinations will match. We're going to just perform this burn, and again it's a tiny change, a 5-degree inclination change, but it is already 164 meters per second of delta V. Again, inclination changes are costly. So there we are, almost there at the burn point. So going to perform that burn. Here we see we are burning parallel to the surface of Kerbin. We are not going to modify the parameters of our orbit too much, just the inclination, the tilt of the circle around the planet, so that now it matches the inclination of Minmus. And now it is easy to plot an intercept with Minmus, because now if we raise or lower our orbit on any point, it will match that inclined orbit of Minmus. You can see it here by rotating the camera. They are, if you look from side on, they're in the same plane. So if we now make a maneuver node to raise, if I can click it, to raise the orbit using the prograde on our new heading, raise that orbit out to the orbit of Minmus, go slightly back, and here we go with a Minmus encounter. Easy as pie, easy as 1, 2, 3, easy peasy. If we did not do the inclination burn beforehand, it would be a little bit more difficult. We would end up slightly below, slightly above Minmus, and here on the distance scales here in the Kerbin system, that doesn't really matter. But if you go interplanetary, the distances are far larger, and you can see there is some inclination changes here and there. They are usually very slight, few degrees only, but because of the huge distances, it is very important to account for it here, especially ELO has a very inclined orbit. If you are making your orbit here, you might very well be in the same ballpark, but because you are so on such a different plane, you're the same distance from the sun, but somewhere else. These are the perils of 3D spaceflight. So, after having watched this video, I hope you understand how to change your orbit, how the prograde, how the retrograde markers work, how you can change your orbit by burning towards or away from the planet, but you also understand why you don't really want to do that, and if you need to match an inclination with Minmus or with another celestial body. I hope I've given you the handles to do that. I'm going to leave this video here. I hope you enjoyed it. I hope you understood what I was talking about. If you do not, please don't hesitate to leave a comment. I will try and explain it a little bit better. Or if you have different questions, post them in the comments, give me an email, whatever you like, and I will try to answer that. Thanks for watching. If you did like the video, don't hesitate to show it to your friends. Maybe they've been struggling with their rockets, their backyard projects. Share it on Facebook, give me a like, give me a subscribe. Any of those things make me eager to make more videos and make me a very happy spaceman. Once again, thanks for watching, and I will see you guys next time. Goodbye.